Hi everyone, we're super excited to be here. My name is Henrik and this is Duncan, and we're both engineers at Lightbend. And we're working in the monitoring team at Lightbend, so today we're going to talk about monitoring reactive applications. There's this rating thing in the application if you downloaded that, so you can rate us before or after. So the agenda today, we're going to talk a little bit about what monitoring is, the traditional way of monitoring applications, the architectural shift, what's going on right now, being reactive applications, of course, and then how to monitor reactive applications, some trends in monitoring and best practice, and then a little bit, finally, about what we're doing at Lightbend. So what is monitoring? Well, monitoring, according to Wikipedia, is to be aware of a state of a system, to observe a situation for any changes which may occur over time, using a monitoring or measuring device of some sort. Now, this, of course, can mean a lot of things, so let's try to narrow it down a little. For monitoring computer systems, we have different categories of monitoring. So first of all, you have this thing called business process monitoring. Basically, you can think of this as if you have a credit card system, if you're a bank, then maybe you want to detect fraud. So you're looking at different transactions, and if there's a purchase being made in Athens, and 5 minutes later it's done in Rome, then you could suspect things, right? You want to keep track of that. That's business process monitoring. You can also think of this as a key performance indicator where you have a dashboard, and you basically just look at one circle if it's green, yellow, or red, and then you can drill down from there to get into the next level, which would be functional monitoring. And functional monitoring could be a credit card transaction, just one, where you do a purchase, and you just want to make sure that this is working as it should. And the final thing is the technical monitoring, where you focus on individual pieces of this, and that could be like the transaction time to MasterCard or Visa. There are different types of monitoring. So one is system monitoring, where you're looking at network traffic or CPU or memory utilization. So that's one thing that we're doing with Lightbend monitoring. Another thing is where you're looking at transaction monitoring. Basically tracing, you want to make sure that you can have IDs following what's going on inside of your application. There's also this thing called performance monitoring, where you want to make sure that you can cram out the most out of your system, so you want to see how it performs under stress, load, things like that. Integration monitoring, which is very popular now when everyone is talking about microservices, where you basically, you can think of this as a dashboard again. There's this, Netflix has this thing called Historics dashboard, where they're looking at how individual microservices are operating, and they're actually doing it from the client's perspective. So the client is basically sending information about how the server is doing. And finally, there's this thing called application monitoring. And for us, that means looking into things like actor mailbox, number of messages in the mailbox, or processing time per message inside of Akka. So traditional monitoring, you normally have these layers, and then you have a request coming in to the web layer that goes on to the next layer, application layer, and all of a sudden you have an exception. Now, this being a synchronous call, just looking at the exception here, which of course there's a lot of layers in this exception. It's a traditional Spring application, so there are a lot of layers. But the exception in itself actually tells you what's been going on up until this point. So just logging this exception and looking at it, you can kind of make sense of what's been happening up until this point. And also, if there's no exception and the request comes back, then it's fairly simple to gather metrics based on this, because it's being a synchronous call, so you know there's going to be a request and a response back, so you can measure times and things like that. So that's the traditional monitoring.
So, oh good, everybody can hear me. So the issue behind monitoring is it's kind of, it's a lot of data, right? There's a lot of stuff going on, and you're trying to distill what's going on. And one of the things I like to do as a reminder is how we got here. and this architectural shift from the 50s into the 60s and so forth as the internet came into being. It started out with DARPA and the notion of a galactic or interconnected global computing network. But this gentleman, Licklider, has some pretty amazing papers on the subject. And that brought us into this idea of distributed computing, which is what the whole reactive movement is, or the reactive manifesto is kind of distilling for the business programmer for the most part, whereas distributed computing was generally for companies like Google and Netflix and all these types of companies. Well, now we see all kinds of smaller businesses or even larger businesses that aren't used to the distributed computing model getting into it. And it started back in the 70s with the mainframe and mini computers being the core hub, like the AS400, and then branched out from there. And so we had to deal with a new way to write programs, a new paradigm, because memory models are different in distributed systems than they are in a local system. But what really happened in the 90s was the whole cloud computing thing, where distributed computing is the technical aspect. Cloud computing ended up being the monetary aspect of it, or the economics. And once business got involved in the 90s to the internet, it kind of opened the doors to the internet as we see it today, and all kinds of stuff started happening. Multi-billion-dollar companies that used to take 20, 30, 40 years to come into existence came into existence within a matter of years. And it really changed the dynamics of our economy. It changed the dynamics of everything. But in so doing, we now have these systems that provide us, you know, the network is the computer, kind of the sun moniker there. But we now have these systems because of things that used to be extremely expensive, like storage and network. And when I was younger, I had a TI-99, and I think I paid $1,500 for the whole system. And I think I had 4K of memory or something like that. And I used to store things on a cassette tape. So, but today, storage, CPU cost, bandwidth cost. For a while, I ran an ISP, and I had 2 T1s coming into my office, and that was $1,500 a month. And now I have FiOS, it's 75 up and down, and it's $100 a month. So the economics drastically changed. And so they allowed a lot of people to get involved in these types of scenarios, whereas before it was a much smaller playing field. And the use of the network increased dramatically. From a company perspective, I like to use this example, these two examples. Amazon, not only did the economics affect us and allowing us to be able to get involved in this arena, but it also shaped how we view ourselves as a company. So Amazon, up until 2007-ish, their retail sales outpaced their infrastructure or network sales, their cloud services. They had to build a whole new infrastructure to support what they were doing. And then 2007 around, their cloud services started to outpace their retail sales. So they had to step back and say, what are we? Are we an online retailer, or are we a provider of services for other people that want to get on the internet? That's a pretty dramatic shift in what you view yourself as. And of course, Netflix and Blockbuster, right? Blockbuster was king of the hill. I remember when Blockbuster was around and Netflix first came out, and my friend said, you have to check it out. And I'm like, seriously? I'm not going to order DVDs through the mail, you know? Maybe if they stream someday, but Blockbuster will be here forever. Blockbuster was a multi-billion-dollar company, and they actually had an opportunity to buy Netflix, I think, for $2 million at one point, but they turned them down. If you look at it today, where's Blockbuster? You know, many younger kids have never even heard of Blockbuster, so it has a dramatic impact on our business model. And it used to be if you had lots of money and you had lots of resources, you were kind of king of the hill. Many of the clients that we work for are rather large, and some of their competition is rather small. They're very agile, they're very quick. Who would have thought a company with 4 guys in their 20s could compete against a billion-dollar company? I mean, that sounds absurd, but it's a fact in today's world. So here we have the microservices chasing after the monolith, right? It's the fast fish that eats the slow fish now, not the big fish anymore. And we have this whole notion of reactive, right? We're all familiar with it, responsiveness. Monitoring very much, in many ways, is akin to being responsive, right? It doesn't matter how good your application is. It doesn't matter how well it scales. It doesn't matter any of that stuff if at the top you're not responding to your customer, if you're not responding to your client in some way. Regardless of how good you are, if your communication is tainted, then you're going to have a problem. I remember a long time ago going through consulting training, and they said perception is reality. And unfortunately, there's some truth to that, but the reality of it is it's the same thing with us in monitoring. We want to be able to be responsive, but there is so much stuff going on in any given system. So, again, we're familiar with these things, but at the top, if we go back to the previous slide, you have responsiveness, message-driven at the bottom, and then it all works together in this pillar structure. And so today what we have is we have the ability with these toolkits like Akka and Play and Lagom and different toolkits, we can begin to build these systems that are isolated and bulkheaded against failure and can scale independently and so forth, have asynchronous boundaries, and they can kind of work together in cohesion to provide a solution. So there's a lot of advantages to being able to design systems like that. Obviously, there's issues too. But one of the problems now becomes is monitoring. How do I monitor these systems? I have systems that have asynchronous boundaries, that have a very lightweight protocol between each other. There's no hard context. And so today, when we get some type of problem, say for example in an Akka system, we get a dump like this, and it's like, okay, what does that mean? It doesn't mean anything to me. How do I find my problem? Where's the error? And so forth. And when you're dealing with Akka systems, you can have systems that have millions of actors in them. And this becomes a very difficult challenge. It's kind of like distilling the noise out of the picture to find what's really important. And I like this little cartoon here. Basically, it kind of gives you an example in an asynchronous environment, what can happen. He says, sometimes I'm shocked to realize how many options I have. The other guy says, oh? Like at any moment, in any conversation, I could just punch the person I was talking to, and all these potentially life-changing events would unfold. It's only mental rules that stop me from punching you or stripping naked or getting on a plane to Fiji. Sure, rules have reasons, but shouldn't you exercise that freedom at least once before you die? Wham! I should have saw that coming. That's the great thing about it, but you couldn't. That's the beauty, right? You don't see it coming. And all of a sudden, we were talking about it yesterday, when it fails hard. So what to do? How do you deal with this situation? Again, just like thinking about building systems and going asynchronous, you got to start to think differently. There's just so many challenges that you have to overcome. That one of the key ones here is in an asynchronous distributed system, you have this whole notion of non-determinism. You can't reason about when something happened. What was the sequence of events that occurred to get me there? You have to be able to take a look at them independently and kind of piece a puzzle together that makes sense. And that becomes very difficult. So one of the ways that you can do this is through the notion of tracing. You can set up, essentially, I'm going to begin to observe at this point in time. And I'm going to tag it, or I'm going to mark it. And I'm going to follow, kind of like a tracker. I'm going to follow where this message goes or where this particular thing is that I'm observing and how it behaves over time in the system. And you may get back information out of order, or you may get back information potentially in not necessarily a synchronous fashion, so therefore you want to be able to piece that together. So tracing, especially across asynchronous boundaries, is one of the ways that you can do it. So you have multiple actors, for example, in Akka, you set up a hot path, or you set up a flow that you think is going to make sense. So that begs another question, is who determines what the hot paths are in my system? right? So monitoring kind of crosses this boundary of business rules. There's so many things going on, I can't watch everything, but I do have to watch what's important, right? You have to make a decision in life. What are the important things I have to focus on? It's what we do every day. And so monitoring is no different. One of the ways that we achieve that is by giving you the ability to set up these things called trace bands that can go across, and then you can kind of get a visual picture of what's going on in your system. In our case here, in our current solution, it's programmatic, and what you can see here is you're going to start a trace within an actor based on some message, and then it's inside, or the internals, we're going to set up a context for you, and we're going to start to track. And then somewhere at the end, somewhere later in your application, you're going to have a closure to it. It's going to be the end of the trace, and we're going to capture histogram information for you that would then allow you to reason about that trace, right? Metric data. So that's one way that you can solve the problem. But wouldn't it be nice if you could tag all along the way, and for an exception, this was the kind of information that you would get in Akka, right? So one of the things that we're taking a look at is this kind of notion to kind of give you a pretty output of your trace.
Okay, so 6 years ago, Google released this paper called the Dapper paper. It's basically lessons learned from monitoring distributed systems. Google have a couple of servers out there. So this was the best practice from how to monitor distributed systems, basically. And TypeSafe, when we started 2011, we had an implementation called TypeSafe Console, which basically is an implementation of the Dapper paper. So the Dapper paper basically prescribes that you have your monitored applications and you instrument them, and based on this instrumentation, you create events. And those events are stored offline into some database. So you can have X number of systems that's instrumented, and they all generate events, and you store them into the database. And then offline, you have analyzers looking at these individual events and trying to make sense. So based on the individual events, you can create metrics, and you can get an understanding of how systems are calling each other, even if it's asynchronous. And you store that information back into the database, and finally you have a query or a read side where you can retrieve this information and present it to the users. So we had this implementation in TypeSafe Console. We decided not to continue with that product because we ended up generating a lot of events, and some customers came back and said, it takes me a minute to get the notification, and that's because if you generate X number of events, the analyzers are going to lag behind, and before they've done their calculation and stored it back into the database, it might be too late. So here, if looking at the Dapper paper again and looking at an Akka application where you have 3 actors, you can see that actor A receives a message 1, and each of these orange boxes are individual events created. So what we did in TypeSafe Console is we said, okay, I have now received message 1, and we created an event and stored that offline. And then we also said, I have sent a message 2 to actor B, that's the told message 2 message there. And finally, when it's done, it says, I now completed message 1. So those 3 events are generated. Same thing for actor B, same thing for actor C, and then actor C replies back to actor A, and it says, received and completed message 4. All of these things can, of course, happen. They will happen asynchronously in Akka, but it could also be over remote boundaries. So it could be different servers generating these events, but they're all going to be stored into the database. So the analyzers, when they look at this, they can make sense of the data, right? So looking at a piece of this, or one of these trace events, what it can look like, this is JSON, so it's not a bit, large data format. But each of these events will have a unique ID. So that's the ID there. They will also have a trace ID. So the trace ID in the example before would be the whole trace from actor A, B, C, and back to A. That's a trace event. So they all belong to the same trace context. They're also pointing back to the parent, and this is very important in a distributed system, that you're always pointing back to what happened before, because the notion of time no longer is working, unless you're Google and you're using asynchronous clock, atomic clocks, where the clock will be the same in the whole distributed system. Then you can use time, but for most of us out there, we can't afford that kind of infrastructure. So instead, we're going to use causal consistency, which basically means that this is the event that happened before me. So even if, if actor B's events are stored in the database before actor A, because that can absolutely happen if there's a garbage collection on the system where actor A exists, eventually we can make sense of this because we can piece these together, right? I know what's going to happen before me. I couldn't find that event right now, so I'm going to wait a little. And then when that event arrives, I can now complete the whole trace and create metrics from that. We also added a lot of other things like nanotime, and that's on the specific server. If you're interested, if you want to make sense of timing, you can do so within the boundary of one server. And we had type annotations that said this is a receive a message, and what actor you're in, and what message, and the message content and stuff like that. So with Lightbend monitoring, we're having a slightly different approach. And this is, instead of generating all of these events and sending them offline, we're trying to capture metrics inside of the application. So internally, we still have these events, but it's going to be inside of the JVM. And then we have our monitoring application listening to all of these events and generating the metrics locally. And then we're sending these events, or this metric information rather, to some other system. So internally we're using Coda Hail, for example, in Takipi metrics, and we can offload the information to Takipi, but with Coda Hail we have a lot of reporters, so you can offload that to Elasticsearch or JMX or SLF4j and what have you. Now, monitoring applications, a lot of times we get a question, how much does this cost monitoring this application? What's the overhead? And that's a very different question to answer, because each of these different systems that you're creating, Akka-based systems, they have their own individual characteristic. Which application is more costly to monitor? An application with few actors with lots of business logic, or an application with several temporary short-lived actors? Now, the answer, of course, is the last one, right? Because if you think, again, about these events being generated, if you're creating millions and millions of actors, we are going to track those actors for you, and everything that's going on, it's going to generate an event. So there will be much more things going on from a monitoring perspective in that type of application than if you're having just a couple of actors and the business logic is taking a long time to run. So there's a cost associated with each event in the application, and it's very hard to predict the performance overhead. There are a couple of ways that you can mitigate this cost that is associated with monitoring. So one of the things is flexible configuration, where you can decide what parts of your system you want to monitor. So let's say you have an actor system again, where some of the parts are generating a lot of short-lived temporary actors. Then you can decide not, by configuration, you can decide not to monitor that part. You just want to monitor the other parts of your system. So that's one way of trying to mitigate the cost that's associated. You can also use sampling. So sampling is that you only want to trace every 100th or 1,000th message to a certain actor. Of course, that's going to generate a lot of less events, and therefore it's cheaper to monitor that system. And there's also a delta approach where you can basically say that, if nothing happens inside of my actor, I'm not going to create any events for that. On the receiving end, it will understand that whatever happened before is still valid because I didn't receive any events. So I can draw my own conclusions based on that. Now, either of these approaches will also mean that you get less insight into your application, or you increase the complexity of your monitoring system. So there's no such thing as free lunch when it comes to monitoring. Okay, so let's switch and talk a little bit about trends in monitoring. And specifically, pull and push. So there are different trends going on, and one is pull-based systems, where you actually have your monitoring system pulling data from the monitored applications, by querying some sort of API, and can get this type of information back. The other one, of course, being push, where the monitored application push data to some endpoint, and it doesn't really care what's going on there. Now, there are different ways of discover what to monitor, depending on your infrastructure. One is where the monitored applications register somewhere in some sort of, in this case, it could be Zookeeper or console. Or you have a cluster scheduler that actually spawns these monitored applications, and you know where the monitored applications exist. So either of those, the monitoring system can then query Zookeeper and say, what system should I monitor, or the cluster scheduler to still receive the same information. Okay, let's put these two together now, pull and push. So if you have a pull-based system, the monitoring system can then ask Zookeeper or console or the cluster scheduler, give me the systems that you want me to monitor. And then it will call these systems and try to retrieve information. And the middle system here is actually down. And in a pull-based system, you now know that something is wrong and can alert. And how can you know if something's wrong? Well, you already have the information about what systems to monitor. So even if DevOps, a DevOps guy decides to restart the system, by subscribing to the information from your cluster scheduler or service discoverability tool, you know that, okay, this is fine because the DevOps guy restarted this, so that's perfectly fine. It's part of the normal operations. But if you don't receive that information, you also know that there's something fishy going on, right? So pull-based systems are quite effective in that sense. Now, for the push-based, you can still achieve the same thing, but you need to add some sort of scheduler to the monitoring system, because the push-based, you really don't know when to receive data. So the monitor application will just push, 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 and you receive data, and all of a sudden you don't receive anything from this one. You need to have a scheduler internally that queries yourself and say, have I received anything from these systems that I'm expecting data from? And based on that information, you can now start to generate alerts if you want to. So what are the differences? Well, data volumes in detail. In the pull-based systems, you can basically say, I just want to know the top 5 things that's going on inside of the application by querying some API. And you get that type of information, and then all of a sudden there's something wrong, and then you can dive into detail and say, okay, give me more information. I want to know exactly what's happening right now. You can basically decide how much data you want to retrieve. In a push-based system, you can't, because the push, you can, but normally you define what data it should push, and it just pushes that information, right? You can still, if you have dynamic configuration, you can instruct the push-based systems what to update what they should push, but it's a little bit more tricky, and the pull-based is more natural. Examples of pull-based systems is Prometheus, that's developed by SoundCloud and here in Berlin, and the push-based system is StatsD, that's used in a lot of places. Another trend that's going on is anomaly detection. And anomaly detection, basically, it's associated with machine learning, of course. You're looking at data. You're having machines or algorithms, statistics. You're using that to determine if something is happening in a system that shouldn't happen. Normally, when you want to fire alerts, you have static thresholds. So you say, okay, if this call takes longer than 1 second, you add that to configuration file. And if it takes longer than 1 second, there will be an event fired saying, this took longer than 1 second. And that's a very crude way of doing things, especially because you normally don't know what hardware you're deploying on, right? So if you're deploying on a small server in Amazon, and all of a sudden you move it to one of the large servers, then the threshold is no longer valid, because the large server is capable of, it shouldn't take that long for a large server. For a small, it could. So by having anomaly detection, you can basically calibrate the threshold automatically. It also gives you things like a better overview of what's going on. If you think of it, you can only have so many dashboards and look at them and trying to figure out what's going on. You don't want to have humans sitting in front of a lot of graphs trying to figure out. And it's actually very hard to figure out what's going on because outliers aren't equal to anomalies. So there's this example in anomaly detection literature where they're looking at number of patients going into a hospital. I believe it's in the UK somewhere. And just looking at this is a couple of weeks, and you look Monday, Tuesday, and so on. And then all of a sudden, there's a huge spike on a Thursday, and then it continues. And normally, as human beings, we just look at the spike and saying, that's the anomaly. And that's not the case, because it's normal for people to come to hospital on a Thursday. On a Friday, however, Friday the week after, it's like a little peak going on, but it's nothing to the Thursday the week before. But the anomaly is actually the Friday. And just looking at the graphs, it's very hard to tell where the anomalies are, and anomaly detection can give you that for free. So a couple of providers, AppDynamics, Rockset, and Vivid Cortex. Okay, Duncan?
Yep. So just kind of a checkpoint, we kind of went through where we got or why we're here because of distributed systems, some of the challenges and some of the trends. And the anomaly detection that Henrik was just talking about is really, really important. You can have two types of anomalies. One is the one that Henrik described, which was a legitimate outlier, but it was not an anomaly, which was the Thursday intake of the hospital. Another one is erroneous data. If you're doing deltas and some of the data that you get back is erroneous, you could have an outlier that shows a false negative or a false positive, and you might assume that's an anomaly, but it isn't. So you got to deal with those things through smoothing algorithms or something like that. So the bottom line for anomalies is kind of getting to the truth. Let's figure out what the real problem was. It may not be what we see visually. And that requires some real thought put into how the system works. A lot of time, it requires training with historical data and so forth to establish a baseline. So, on to a different topic, configuration. For us, one of the things that we do to get around the issue of there's so much going on is we give you the ability to configure how you want to monitor. And we have a number of ways. You can do it by class and path and wildcard and so forth. You can do grouping, you can do includes and excludes and et cetera. So it's a pretty robust configuration for our monitoring support, and this is an example. We also have kind of like static dynamic configuration where based on a path, you can group actors together on the fly to get out an output. So for example, here we have question mark star, and you're going to get a group name back for that scenario. But one of the things that we're taking a look into is really runtime dynamic configuration, right? The type-safe config is immutable, and there's a lot of reasons for that. But wouldn't it be nice if, especially from a monitoring perspective, if while you're observing your system and you begin to think that there might be a problem in this location, you want to turn up the monitoring a little bit during the runtime environment. Those types of scenarios. So as you begin to focus in on where you think a problem might be, initially you weren't paying the cost for a more detailed observation, but now you recognize a hotspot or whatever. Let's zoom in a little bit and see what's going on. Dynamic configuration could provide you those semantics, and there's already examples of it out there. There's toolkits out there that provide it, but things like typed properties, et cetera, are some of the things that you're going to want in that, and that's one of the things that we're looking at as well. The other thing is self-monitoring. So self-monitoring is, the best way to think about it is you monitor yourself every day, right? If you start to feel sick, you start to get a cold, you might go take some, natural remedy, or you might go to the pharmacy and get some cold medicine or whatever. When that cold starts to get worse and you start to feel really sick, you might think, hey, do I have the flu? And at that point, most likely, you're going to give your doctor a call. So up until the point that you call your doctor, you have been self-monitoring. You have been taking your temperature. You have been kind of just saying, how do I feel? There is a point at which you say, okay, this is beyond my ability to self-care, and I'm going to go to a professional. So one of the things that we're also taking a look at internally is self-monitoring, where an actor outside of the monitoring system, or it would be our monitoring solution that provides it, but the actor kind of takes a look at itself every now and again, and it really doesn't complain until it feels the need to, and then says, okay, I think I might have a problem. In the big picture, it may not be a problem, but that actor is kind of looking at itself and saying, okay, I want to notify someone else. So another way to think about this is your feedback control loops. So the example here is we have an actor that has some type of intelligence baked into it, and it detects a disturbance, okay? As a result of that disturbance, it's going to execute a measurement and provide that measurement either to itself or to an external source, who then is going to make an adjustment. And that's a loop that happens. It could be scheduled, it could be time-based, whatever, until such a time that the disturbance is gone, right? And so it's kind of like programming large systems, right? Do it in small chunks. If you can capture the problem when it first starts and begin to adjust or compensate for it, then you might be able to stop or at least mitigate the larger wave that could result from not handling it quickly. And that's the whole idea behind resilience and self-healing and reactive in the Reactive Manifesto, and the same idea in monitoring. This loop, the closed-back control loop, is, I don't know, 50 years old at least. You see it in your thermostat on your wall and so forth. It's in hardware, it's pretty common. But bringing that into software is one of the things that we're taking a deep look at. The challenge becomes is for a generalized monitoring solution, it's very difficult to abstract some of these concepts in such a way that they apply to all these different types of use cases, because every customer has a different use case. So some of the challenges. Some of the best practices for monitoring is the first and foremost, most important thing is understand your system. Okay, you would be amazed at how many people really don't have a good understanding of the software that they're actually working on. And that's crucial, because that's going to let you know what's important and what's not important in your system. What are the hot paths? What are the important routes that I want to pay attention to? So that's crucial. Understand whatever tool you're using, read the manual, right? Understand how it works, all the details of it, all the features of it, and so forth. Being configurable, right? Your tools, you want them to be configurable. You want them to be elastic. And that's one of the things that we're pushing pretty hard. Deltas. In the energy industry, capturing delta readings is commonplace, right? You don't, if you're, for example, reading a meter every 2 seconds or every 5 seconds and the reading has not changed, then you do not persist that value. The only time you persist the value and timestamp it is when the reading is actually changed. So that's a huge decrease in the amount of data that you have to store. So capturing deltas is one way. The traditional elastic approach where you're capturing everything, you can deplete your resources pretty quickly. And the only person that can answer the questions is, do I need all that data, or the data scientist, right? Or the business, so to speak. So you have to be able to take a look at your system from that point of view. Sampling, as we had mentioned earlier, obviously capturing enough data. If you scale back too far, then you don't have enough data to reason about what the problem is. Okay? Multiple channels for notification, right? What's the purpose of this at the end of the day? You want to let people know that what is the health of the system, or is there a potential problem brewing? So being able to notify the right people is very, very important. And reports, graphs, all kinds of pretty things for DevOps and the different people that are responsible for keeping the system up and running. are important too. So, and you don't want your monitoring system finally impeding your application. So running your monitoring tool on a different machine and so forth is a pretty important thing as well.
Okay, let's talk a little bit about Lightbend monitoring and what we've been doing. The project started a little more than a year ago, and currently we integrate with Akka actors, and Logom, our new microservice framework, it's circuit breakers. So based on that, we're generating metrics, events, and traces. We have support for various backends. As I said before, via the Code Hail reporter, we can generate a lot of different output channels. And we also have Takipi integration, which is a really cool tool. If you haven't seen that, take a look. Monitoring requires a subscription with Lightbend. Okay, so that's what we had. What's on the roadmap then? Well, we're going to add information about dispatchers and thread pools. Working for Lightbend and being an employee at Lightbend, I do quite a lot of consulting as well. And going out to customers, one of the biggest mistakes that newbies do with Akka applications is that they run all the actors in the same dispatcher, the thread pool. Basically, what happens is, you use the default configuration, and then all of a sudden they call and say, my Akka application is no longer working. It's not responsive. Didn't you tell us? Didn't you promise us that this is asynchronous and it's going to solve all the problems out there? We kind of did that, but not if you run everything in the same thread pool. Because what happens if you call a database? Eventually, if the database it's a synchronous call. So what happens is that you're waiting for that call to come back. You're basically locking one thread, right? So whenever you're communicating with an external system, you want to make sure that runs in its own thread pool, in its own dispatcher. So that's one of the patterns, actor patterns or Akka patterns that should be applied for the first thing you do. And by providing information about the dispatchers and thread pools in monitoring, we can easily, you run your monitoring tool and you just look at it and it will tell you that you probably need to do something with your dispatchers. It makes it obvious. Another thing that we're going to do is this, what we've branded flows, which basically is, features and streams. And you can also think of actors as a kind of a flow-through system, where you have, your transactions are flowing through your system. As right now, we only have Akka actors monitored, but we're going to add this for features and streams as well. So you get the same type of information regardless of what you're running under the hood. And we're also going to add distributed tracing using Zipkin or something similar. We're going to add increased logom support and Akka HTTP support. Okay, I think it's time to wrap up. Thank you for listening. And Lightbend has its own booth down there, and the whole monitoring team, Duncan and myself and Bjorn and Peter, we're going to be there the next hour. So we'd be happy to answer any questions you might have that are related to monitoring or Lightbend monitoring or Akka or whatever. Thank you, guys.